Welcome to day 13. We got packet page 7 and one problem from page 700 in the textbook for homework. So for your homework answers, it's smooth as long as the parts of the derivative um, are not simultaneously 0. So t equals 0 is the time when they will be 0 simultaneously. So therefore, we're going to be smooth everywhere except for there. In 2a, just take your derivative of each of the parts. In 2b, first we got to sub in t squared for t and then take the derivative. In 3, take your derivative of the parts, then your second derivative. In 4, take your antiderivative, and probably what I have boxed there is the most common way, or you could technically add a separate vector for the constants, but probably the boxed way is the most common one. In 5, right, everyone should have tan t plus c1, but then the second part, that's either arc cos, or you could say it's minus arc sine. So either of those would be fine, plus your constant. If you've got a definite integral, just do the antiderivative and sub in your values, basically evaluates the definite integral for each of the parts of the component. For 7 and 8, use the vector that they give you to evaluate the constant. So do antiderivative. Just note there's technically a little u substitution for the x part. And then use the given, the initial v, to find your constants. In 8, since we start with the second derivative, we'll have to find our constants both steps of the way. In 9, because we're starting at rest at a position of 0, 0, that means we know our initial position is 0, 0, and our initial velocity is 0, 0. So we can use those two things. Eventually, we'll get this for our position, and then just sub in 2 to find the position of the particle at 2 seconds. In 10, you could graph the original. You've got your derivative function, sub in 1, and that will give us our velocity vector, which is the one labeled v there. Remember, velocity is like if you released off the line at that instant, that's the path you would keep going. And then the acceleration vector is like where you're being pulled. So if you take the second derivative, sub in the ones, we get the 6, 2 for the acceleration vector. And then your speed, you got your square root of each of the parts of the velocity vector that were evaluated when t equals 1. And similar idea for this one. And 12 was the same idea as well. In the textbook one, remember x is really r cos theta, so fill in your 3 times 1 minus cos theta for r. Do your dx d theta, and then do a similar thing for y to get your dy d theta. And then our derivative is dy d theta over dx d theta. So you can put those together. That's what I have in that second last line. Then we want to evaluate at pi over 2. So if you put pi over 2 in, you get negative 1. And the picture was up there, and that's the tangent line sketched in at pi over 2. So we're going to be in the day 13 notes in the packet. So today we're going to model projectile paths. You may have seen elements of this in physics if you take physics. So these are our equations to find our vector valued function for our projectile path. You've got the exponent, notice involves cos, the y component involves sine, and also has to do with velocity, or sorry, with the gravity constant. They both involve the initial velocity as well, and the y component has the initial height in it as well. So where are these coming from? So if we think of that v0 as being that hypotenuse vector there, the initial velocity. If you did sine of theta, that would be y over v0. We'll multiply the v0 over, you get v0 times sine theta, and that's our vertical velocity for our object. Similar idea for cos theta, do the adjacent over the hypotenuse, multiply over. Well, if you want to find your horizontal component and the distance that it covered, we need to do a rate times a time. Well, we just found our rate was v0 cos theta, multiply it by our time, and that's how we get what we have in the x component up on the top of the page. Now for the vertical, start with your acceleration of gravity, because that's constant. Antiderivative of that would be g of t plus some constant, but that constant would just be our initial velocity. Do that, which the initial velocity we found above was v0 sine theta. Do that antiderivative, and you'll have another constant at the end. Well, since that's the position function, that constant should just be your initial height. So that's where each of those things comes from. So if we flip to the next page, we're going to have a scenario that we'll look at several different questions for. So we got Peter swings a bat of a baseball and makes contact 3 feet above the ground. The angle of elevation is pi over 4. Initial velocity is 100 feet per second. So for our vector valued function, we need to do our initial velocity times cos theta and then times t. So our initial velocity we had was 100. Cos of pi over 4 is 1 over square root of 2, or rationalized square root of 2 over 2, and then times t. In calculus, we tend to use feet more than meters. In physics, you usually do meters and use negative 9.81. In feet per second squared, the acceleration of gravity is negative 32. So we are going to have 1/2 times negative 32, which, so in other words, negative 16, and then our t squared for the first part. And then we have our initial velocity times sine of pi over 4, which also is square root of 2 over 2, times t, and then our initial height, which is plus 3. So we can neaten that up slightly to be 50 square root of 2 t, comma, negative 16t squared plus 50 square root of 2t plus 3. So we want to know when the ball reaches the maximum height. We've seen a ton of times throughout this course, if you want to find a max, we want to take the derivative, and we want to see when it switches from positive to negative. So if we do the derivative of our y component, we're going to have negative 32t plus 50 square root of 2. We'll set that equal to 0. Oops, I forgot my 0 in my 50, sorry. And if we subtract the 50 square root of 2 over and divide by 32, we'll end up with a positive 50 square root of 2 over 32. Or in other words, that's 25 square root of 2 over 16. Now, if you did that as 3 decimal places, that would be 2.210. So we've got to put that on a number line. So this is our derivative of the y component is linear with a negative slope. So if you're linear with a negative slope, on the left you should be positive, on the right you should be negative. We should put our labels on of y prime of t, and this is t. So we can say there is a max at t equals 25 square root of 2 over 16, since g prime of t switches from positive to negative. Well, remember, we really wanted to find the max height. So we've got to take that 25 square root of 2 over 16 and sub it back into our y component. So we're going to have negative 16 times 25 square root of 2 over 16 squared plus 50 square root of 2 times 25 square root of 2 over 16 plus our initial height of 3. And when we put that into 3 decimal places, we get 81.125 feet. So that is the highest that the ball ever goes. So same scenario, but now we want to know if Peter will get a home run. And at the home run fence, it's 12 feet, and it's 300 feet away from home plate. So basically what we need to know is how high is the ball when it reaches the 300-foot mark. Well, 300 feet is a horizontal distance. So we'll start out, and in case you were wondering, this just wants to know when x is 300, is our y 12 feet or greater? So we're going to take that 300 and set it equal to the horizontal component, because what this will do is it'll tell us at what time the ball reaches 300 horizontal feet out. So if we divide by 50 square root of 2, this will give us 6 over square root of 2. And if we rationalize, we'll get 6 square root of 2 over 2, which is the same as 3 square root of 2 seconds for t. Well, then we need to know what is our vertical component at 3 square root of 2 seconds, because that'll tell us how high the ball is when it reaches that horizontal distance. So we'll have negative 16 times our t value squared, so 3 square root of 2 squared, plus 50 square root of 2 times 3 square root of 2 plus 3. And you could either do this in the calculator, or it ends up reasonably nice by hand as well. When you sub it in, you end up getting 15 feet. So we would say yes, it is a home run. So same scenario, but this time we want to find the total distance that the ball traveled. So that the ball is not traveling just horizontal or just vertical. It's this curved path here. So we've basically got to find the length of our curve. So first thing we need to know is, when does the ball hit the ground? Because that's when we would want to stop our path. So it's going to hit the ground when the height is 0. So we're going to do 0 equals negative 16 t squared plus 50 square root of 2t plus 3. because that's our vertical component. This is messy, so we'll do quadratic formula. T is going to equal negative b, so negative 50 square root of 2, plus or minus b squared, so 50 square root of 2 squared, minus 4 times our a times our c, and we're all over 2 times our a. So that value of t, when we sub it in, we'll get two answers. We'll get minus 0.042, and we'll get t equals 4.461, and both those are seconds. Well, you can't have a negative seconds, so we know we're going to hit the ground at 4.461 seconds. So now we're going to use the arc length formula for vector valued functions. And if we look at the bottom of the page, we have that here. So it's just the integral, and you're doing the square root, and it's the x components derivative squared plus the y components derivative squared. This works as long as it's smooth and it doesn't intersect itself. It could potentially intersect itself at the endpoints, but in the interior, it shouldn't. And notice this is the exact same formula as our parametric arc length formula. So if we go back up here, that means we're going to have the integral from 0 to 4.461. We'll have square root. Our derivative of our x component, just as a reminder, this was our x component. So its derivative, we're going to have 50 square root of 2. The y component's derivative will have negative 32t plus 50 square root of 2. So those are what we're going to be squaring under our radical. So we'll have 50 square root of 2 squared. We'll have plus parentheses negative 32t plus 50 square root of 2, close parentheses, squared, and then we'll have a dt at the end. And this is something you would not be expected to evaluate by hand. You would just sub it in the calculator. When we put it in the calculator, we get 362.863 feet. So we're going to go to the bottom of the next page, or maybe it's the only thing on the next page, this question, where we've got r of t is equal to 2 cos t, comma 2 sine t. So we want to find the length, so we're going to use the formula that we just saw. Now, just note, so you can get a sense of what the graph looks like, when you put in 0 here, you would get 1 comma 0, so we're starting here. And then when you put in pi over 2, you would get 0 comma 2, so then we'd go here. And then this would be the pi, this would be the 3 pi over 2, and then back to 2 pi. So that's the direction that we're going. So notice it's smooth, it's not intersecting itself other than at the endpoints. So we're just going to go 0 to 2 pi. We'll have square root. We're going to have our x parts derivative squared. So 2 cos t's derivative is negative 2 sine t squared plus derivative of 2 sine t would be 2 cos t squared and then dt. And this we could do by hand. If we square those, we get 4 sine squared t plus 4 cos squared t dt. So this is square root of 4 times square root of sine squared t plus cos squared t dt. Well, this neatens up to just 2 dt because sine squared plus cos squared is just 1 and square root of 4 is 2. So we're just going to have 2t from 0 to 2 pi. So we'll have 4 pi minus 0, or in other words, 4 pi is the length of our curve. Now let's think about why this makes sense. Our graph was actually a circle. It had a radius of 2. And the length is the same as saying the circumference. Circumference is 2 pi r. 2 pi times 2 gives us 4 pi. So it seems like our formula does work. It gives us what we think we should get. That's it for this video. So you got tonight's homework, and then I would also suggest doing a bit of the review sheet as well. Have a great rest of your day.